All right, so now that we've learned the delta S of reaction under standard conditions, we can calculate delta G of reaction under standard conditions, right? So there are three ways to calculate delta G of reaction under standard conditions. So the first one here is by using this specific reaction, right? So it's equivalent to delta H of reaction under standard conditions minus T times delta S of reaction. And the second one is similar to how you would determine the delta S of reaction under standard conditions by taking the sum of the delta G of formation of the products and then taking the sum of the delta G formation of the reactants and then taking the difference between the two. Okay, and the last one here, number 3, is basically similar to the Hess's law, in which you add up the reactions, chemical reaction equations, and see if you get the actual overall reaction that we want. Okay, so if you're adding 2 reactions to get the third reaction, then you'll also add up the delta G values to get the delta G of the desired reaction equation. Okay, so we'll take a look at every single one of these in a little bit more detail. All right, but first let's talk about delta G of formation. All right, so delta G of formation, or the free energy of formation, is the change in free energy when 1 mole of a compound forms from its elements in their standard states. Okay, so for pure elements, we designate the value of 0 in their standard states. Okay, so for example, hydrogen gas, oxygen gas, nitrogen gas, and carbon will receive the value of 0. Okay. And these values will also be given to you on the test. Okay, so these are tabulated values. All right, let's take a look at this one example here using method 1, using the first equation. All right, so one of the possible initial steps in the formation of acid rain is the oxidation of sulfur dioxide to sulfur trioxide, given by this chemical reaction equation. Calculate delta G of reaction at 25 degrees Celsius and determine whether the reaction is spontaneous. All right. So we're going to use the first equation here. All right, so delta G of reaction is equivalent to delta H of reaction minus T delta S of reaction. Again, all in their standard states. Right, so the first one here, delta H of reaction, can be determined by using delta H of formation. Okay, so we have products minus reactants. Okay, and we'll do the same thing for delta S of reaction. Right, so products minus reactants. All right, so for the products, right, we only have one here, sulfur trioxide. So we have 1 mole of sulfur trioxide multiplied by the delta H of formation, which is negative 395.7. And then we're going to subtract the reactants here. So we have 1 mole of sulfur dioxide, which is negative 297, plus oxygen, which is 0. All right. So the delta H of reaction is going to be equal negative 98.7. And this is in kilojoules. Okay. And we'll do the same thing for delta S of reaction. We have products. So we'll use this information. All right, so for sulfur trioxide, we have 256.8. And then we're going to subtract the reactants here. So that's 1 times sulfur dioxide, which is 248.2. Plus oxygen, which is 1/2 times 205.2. And that gives us negative 94 joules per Kelvin. All right, so notice that this is in joules and delta H of reaction is in kilojoules, so we can convert this to negative 0.094 kilojoules per Kelvin. All right, and we're supposed to multiply this by the temperature, right, because this is temperature times delta S of reaction. So our temperature here is 25 degrees Celsius. To convert that to kelvins, we have 298. So that's negative 0.094 times 298. And that would give us negative 28.01. So now we have the values of delta H reaction and the temperature multiplied by delta S reaction. So now we can find delta G of reaction. So that's negative 98.7 minus negative 28.01. And that gives us negative 70.7. All right, so is this reaction spontaneous or non-spontaneous?
Spontaneous.
Spontaneous because it's a negative value. Yes. All right, so for the reaction in example 18.6, which is basically the previous example, estimate the value of delta G reaction at 125 degrees Celsius. And is it more or less spontaneous compared to the previous example? All right, so we'll use the same equation here. So delta G of reaction is equivalent to delta H of reaction minus T delta S of reaction. All right, so what was the value that we got earlier for delta H of reaction? So earlier we got negative 98.7 kilojoules. And then we're going to plug in 125 degrees Celsius for temperature in kelvins. So that's 125 plus 273. So we have 398 kelvins. And what was the delta S of reaction? I think it was negative 94 in joules, right? So we divide that by 1,000. So we have negative 0.094 kilojoules per Kelvin. So we get negative 61.3 kilojoules. All right, previously, what was the number that we got for delta G of reaction? Negative 70.9? 0.7? All right, so based on these values, is this reaction at 125 degrees Celsius more or less spontaneous? It'd be More or less spontaneous. It would be less is spontaneous. It's it's less negative. I think it was more negative, because when delta G is negative, then we have spontaneous reaction. So if it was less negative, then it would be less spontaneous. So this is less negative, and therefore less spontaneous. All right. So less spontaneous. All right, so now we're going to be using method 2 here, right? So ozone in the lower atmosphere is a pollutant which can form by the following reaction involving the oxidation of unburned hydrocarbons. So we have methane being burnt here, turning into carbon dioxide, water, and ozone. So use the standard free energies of formation to determine delta G of reaction, okay? So we're given the equation here, right, for delta G of reaction. So this is actually a lot simpler than the previous method. So we're just summing up all the delta G of formation of the products and of the reactants and taking the difference. So for the products, so let's take care of this first. So we have 1 mole of carbon monoxide or carbon dioxide, which is negative 394.4, plus 2 moles of water, which is negative 228.6, plus ozone, which is 163.2. 4 times 163.2. All right. And this gives us negative 198.8. So that's for the products. For the reactants, so we have CH4, which is methane, negative 50.5, plus 8 times 0, right, which is negative 50.5. All right, so now we're going to take the difference between the products and the reactants here. So negative 198.8 minus negative 50.5 gives us negative 148.3. All right, and this is going to be in kilojoules. All right, again, this is a negative value, and so it's going to be spontaneous. So here's a cleaner version. All right, now let's take a look at method number 3. So method number 3 is related to Hess's law, in which you just add up the chemical reaction equations, and then you get the value of delta G of reaction. All right, so if a chemical reaction equation is multiplied by a factor, then the value of the delta G reaction is also multiplied by that same factor. Okay, so for example, if we have A plus B turning into 2C, and you want to multiply that by 2, this turns into 2A plus 2B and 4C. So because we multiplied the reaction equation by 2, we'll also multiply the delta G reaction by 2. Okay. If a reaction is reversed, then the delta G value changes sign. Right. So if we were to reverse this equation right here into 2C breaking down into A plus B, then we just change the sign from positive to negative. Okay. And don't get this confused with equilibrium constant K, capital K, right? For that one, when you reverse a reaction, you take the reciprocal of the value of K. But for delta G of reaction, you just change the sign, okay? The opposite sign. All right, if a reaction can be expressed as a series of reactions, the sum of the delta G values of the individual reaction is the delta G reaction of the total reaction. So this is related to Hess's law. Right, so for example, if we're trying to determine the delta G of reaction for this specific reaction, can we get this reaction from reactions 1 and 2? Right, and if we can, then we can just add up the delta G values to get the delta G of the reaction, right? So in this case, since these compounds right here are on the opposite side of the arrow, this will be subtracted from the 2C here, right? And B will be subtracted from 2B. And then you add them all up, we have A plus D equals B plus C, which is basically what we want here, right? Same equation. And so we just basically added the two reaction equations. And so in order to determine delta G of reaction, we also add up the delta G reaction values, right? So 30 plus negative 20 gives you a positive 10 kilojoules, right? So this is the delta G of reaction for this.
So you're literally just adding?
Yep. All right, so here's the next problem. Find delta G of reaction for this specific reaction, right? So we're given three different reactions here at the bottom with their delta G reaction values. So how do we get the delta G of reaction for this specific reaction? All right, so basically the first thing you want to do here is determine what we have on the product side, right? So we have C3H8. So your source of propane is going to be this equation right here, right? Because we have C3H8. But this is on the left-hand side, reactant. So we have to flip it. We're going to have to reverse it. And this will give us a positive sign. All right, and then for the second equation here, we have source of carbon. And we know carbon is on the reactant side, so we don't do anything here except we multiply it by 3 because we have 3 moles of carbon, right? So this becomes 3 here, and 3 here. So we multiply this by 3 as well, okay? And then for the third equation, is going to be our source of hydrogen gas, okay? So we have 4 moles of hydrogen gas, but in this equation we only have 2, so we have to multiply this entire thing by 2. So because we multiplied the chemical reaction by 2, we will also multiply this delta G reaction by 2, okay? So now we have positive 2074 plus 3 times negative 394.4 plus 2 times negative 457.1.
So it doesn't matter, like, if you physically show that you cancel out the things that cancel out, or are you literally just looking to find the number?
So the answer here is negative 23.4 kilojoules. All right. All right, so we're going to omit sections 9 and 10, and that basically ends chapter 18.